So, today we are going to discuss few numerical problems. Let us look at the problems one after other. The first problem: whenever you see a problem, read the problem very carefully and a bit slowly, so that you can first comprehend the problem and then only you start answering. So, the first numerical, it says a draw frame is fed with 8 slivers. The slivers are coming from 2 sources. This is what is important. The mass CV of the slivers from the 2 sources are 2.8 and 3.2 respectively. Now, the question is coming: if 4 slivers from each sources are fed and drafted together, what will be the CV percentage of the combined slivers at the feed end? So, there are 2 different sources from which the slivers are coming, maybe from 2 different carding machines, and therefore, due to some reason the sliver CVs are not exactly same, but we are taking 4 slivers from the first source and another 4 slivers from the second source, and then 4 and 4 total becomes 8 we are feeding. So, how do we go about this solving this problem? First thing is, variance has additive property. This is what you should all remember, that variance is what is variance? It is square of standard deviations. In this case, CV percentage squared is also known as relative variance. So, the property of variance and properties of relative variance are similar. So, we apply this rule, that is, the variance has some additive property. If this is true, then CV percentage of the combined sliver we can write, this is will be square root 2.8 square by 4 plus 3.2 square by 4. Why this 2.8 and 3.2 are coming? Because one source is having CV 2.8, another source having 3.2. So, 2.8 squared is the variance divided by 4, because there are 4 slivers coming from this source and there are another 4 sliver coming from the other source. So, what we do? We add this variances and then we divide by 4, because there are 4 slivers from each source. So, if we go by this rule, then we can see that the CV is coming to be 2.12. So, while that means by combining this 8 slivers, 4 from one source, another 4 from the other source, the final CV is coming to be less than 2.8, and that is because there is a doubling action which is there within the draw frame, and hence while we are combining this 8 slivers at the feed point, this sliver CV, combined sliver CV is coming to be 2.12. Now, let us go to the next part of the problem. After drafting, the CV percentage of the output sliver was found to be 4%. Okay. So, though at the input point the combined CV was 2.12, at the output the sliver CV was found to be 4%. How much variation was added by the process? That basically means, if the output CV is more than the input CV, that means the process is generating some variability into the product, and we have to estimate what is that variability, how much it is. So, again we apply this rule now, that is, the output variance 4 square is equal to the input variance 2.12 square plus the variance that will be added by the process, that is C v square process. So, this is going to be the formula. Now, from there we have to find out what is the C v that has been added due to the process. So, this is now very simple. C v of the process will be under root 4 square minus 2.12 squared, and therefore, if we take this differences and then take the square root, then we find the value to be 3.38. That means, the process is adding a variability which is equivalent to 3.38. So, this is how we can solve this problem, and now we go to the next problem. Read the problem again now. Two slivers made from 38 millimeter fibers are undergoing drafting in a drafting zone. So, a sliver made from 38 fibers is undergoing drafting in a drafting zone. The distance between the nips is 20% more than the fiber length. So, one sliver is getting drafted, the sliver is made of 38 millimeter fibers, but the distance between the nip is 20% more than the fiber length. If the draft is 5, determine the location within the drafting zone where both fast and slow moving fibers will be exactly same. So, read the problem. So, we have to find out that within the drafting zone where the number of fibers moving at back and front roller speeds are exactly same. Within the drafting zone, we have fibers moving at slow speed as well as fast speed. So, the solution is shown below. We know that the distance from back nip for the fast and slow moving fibers are same is given by the following equation. If you remember the theory part of the lecture related to this particular problem, then you will be able to recall that the distance from the back nip where the number of fibers moving at back and front roller speed that exactly same is given by this formula x equal to L into z plus E by z plus 1, where if we remember this, then it is only substitution of the values in the formula. So, the problem is otherwise very simple, one has to remember this particular formula. So, in this formula you see everything is given. The value of L is 38 is given. The setting E, it has been said it is 20% more than the fiber length. That means, basically E is 0.2 and the draft is also given 5. So, Z is 5. So, if we have these values, we simply substitute the values of L, E and Z in the formula and straight away we get the answer. So, if we put these values in the formula, we get x as 32.9 So, that means within the drafting zone at a distance of roughly 33 millimeter from the back nip line, the fibers moving at front and back roller speed will be almost same. This is how we can find it out. All right. So, from there let us now go to the next problem. The problem is the bottom middle roller of draw frame drafting unit was found to be eccentric. So, in a draw frame, the bottom middle roller was found to be eccentric. The diameter is 40 The total draft and the break draft are 6 and 1.2 respectively. What will be the wavelength of the periodic variation generated? The question is, what is going to be the wavelength of the periodic variation? Eccentric roller, as already has been discussed, that any eccentric roller will generate periodic mass variation in the drafted product. We need to know what is the wavelength. If we know the wavelength, then from there we can find out what is the source of generation of drafting wave. Generally in the E star spectrograph, we will be able to find out the wavelength, and from there if we go for back calculations, we will be able to locate the source. In this case, the source anyway has been told, we need to find out the wavelength part. So, how do we go about it? First we find out what is the circumference of the middle bottom roller. Its diameter is 40 mm, and therefore, circumference is going to be pi d, and therefore, it is going to be pi into 40, and hence it is 125.66 mm, close to 126 mm we can say. Now, the middle roller, there is a draft in the front zone. We have to find out how much draft is there in the front zone, because whatever periodic variation that the middle roller is going to generate, this periodic variation is going to be extended. That is, the wavelength that gets generated by the middle roller will be extended, because there is draft in the front zone in front of it. So, we need to know how much draft is there in the front zone. So, total draft is 6, and the back zone job or the break draft is given to be 1.2, and therefore, the draft in the front zone is going to be 6 by 1.2, which is equal to 5. That is the draft into front zone. That means, the wavelength that the middle roller is generating will be stretched out 5 times, because 5 is the draft in the front zone. So, wavelength of the periodic variation is going to be therefore 125.66 into 5, and if we do this, we get a value 628.3 mm, or we can say approximately 63 centimeter. So, if the middle roller is eccentric due to any reason, in the drafted sliver there will be periodic variation, periodic mass variation, which will be, its wavelength will be close to 63 centimeter. If we say that instead of middle roller, the front bottom roller having same diameter becomes eccentric, front bottom roller. So, that roller is eccentric. What will be the wavelength of periodic variations? So, instead of middle roller, the front roller is eccentric. So, if the diameter remains same, the circumference of the front roller also is going to be pi into 40, that is 125.66 mm. So, same, as there is no drafting after front roller. So, the wavelength will remain same, it is not going to be stretched out in this case. So, wavelength of periodic variation is going to be 125.66 mm, that is we can roughly say 12.5 centimeter. So, you see that when the front bottom roll is eccentric, whatever is the circumference, that is going to be the wavelength of the periodic variations. If the middle bottom roller is eccentric, then the periodic variation is going to be little extended over a larger length. How much will be larger? Whatever is the draft in the front zone, the wavelength getting generated by the middle bottom roller has to be multiplied by that draft. it will get extended. So, from this logic we can say if the back bottom roller is eccentric, it will also generate periodic variation with a certain wavelength, but that wavelength is going to be extended or stretched out by the draft in the back zone and by the draft in the front zone, and therefore, it will be wavelength is going to be stretched out over a longer length. So, this is how we can find out the wavelength due to periodic variation. Now, see another problem. This problem is, let us say there are 2 polyester and 6 viscose rayon slivers of same count are blended on a draw frame keeping draft 8. In the second passage, 4 slivers from the first passage are further blended with 2 combed cotton slivers of the same count keeping draft 6. What is the viscose, polyester and cotton percentage in the final sliver? So, that means there are 2 passages. In the first passage, we are feeding 2 polyester and 6 viscose rayon slivers. So, there are 8 slivers being fed and draft is also 8. The sliver count is not changing both at the input and at the output. So, after the first passage we get a PV sliver. So, let us first find out what is going to be the polyester percentage and viscose percentage after first passage. So, as shown that the viscose fiber or viscose in the sliver after the first passage is going to be 6 by 8 into 100, that is 75%. We are not taking into account the count of the sliver because counts have not changed. So, simply by dividing by the number of slivers, we can find out what is the percentage of viscose. 6 slivers viscose rayons are being fed and there are total 8 slivers. So, viscose percentage is going to be 6 by 8. The polyester percentage will be how much? Polyester, there are only 2 slivers and total slivers are 8, is going to be 2 by 8 into 100, that is 25%. This is how we can find out the polyester and viscose percentage after first passage. Now, what is happening? 4 slivers that we have already produced, that is 4 PV slivers and 2 now new cotton slivers are being blended together now in the second passage. So, now we are feeding 4 slivers coming from the breaker draw frame or the first passage, and we are taking 2 cotton slivers now and putting them together on the draw frame and drafting them together. So, after second passage, the respective percentages will be for viscose. If we want to find out for viscose, so because the sliver count is not changing, therefore, it is relatively easy to solve. Viscose percentage will be, there are 4 slivers having viscose fiber, 4 PV slivers are there. In the 4 sliver, each sliver is having 0.75 proportion of viscose. Therefore, the total viscose content in the final sliver is going to be 4 into 0.75 and the total number of slivers in the second passage is 6. This is, you should remember that in the second passage we are feeding 4 and 2, total 6 slivers, and the draft we have not changed, draft is also 6. Therefore, viscose is going to be 4 into 0.75 divided by 6 into 100, that gives you a value 50%. Next, polyester. Similarly, there are 4 PV slivers are being fed. Each PV slivers, the proportion of polyester is going to be 0.25. So, in 4 slivers, the proportion is going to be 4 into 0.25, that is equal to 1. and there are 6 slivers total being fed. Therefore, polyester percentage in the final sliver is going to be 4 into 0.25 by 6 into 100, that will give you a value 16.6%. And last comes the cotton percentage. So, there are 2 cotton slivers, both the slivers are 100% cotton. So, now in this case it will be 2 into actually 1, we have not mentioned 1. So, it is basically 2 into 1 divided by 6. So, it is basically 2 by 6 into 100, that is 33.3%. Therefore, we can calculate viscose percentage, polyester percentage and cotton percentage. So, after first passage the polyester percentage was 25%, but after second passage the polyester percentage has gone down 16.6%. Viscose percentage after first passage was 75%, but after second passage it has gone down to 50%. So, that is the now the final proportion of the fibers in the slivers, 50% viscose, 16.6% polyester and 33.3% cotton. This is how we can calculate. From there we go to another problem now. 4 slivers of 0.10 Ne, now the count is Ne, and 2 slivers of 0.12 Ne are drafted together to produce drawn sliver of linear density 5.5 kilotex. So, this is a mixed unit. The problem was given so that you know the conversion formula, Ne to tex or tex to Ne. This you should always remember. Few formula one has to memorize and remember. This constants that we use for switching from one counting system to another counting system, you must remember. So, now in this case 4 slivers and 2 slivers, they have different counts, total 6 slivers are there, they have been drafted and the final sliver has to be 5.5 kilotex. How much draft is required? So, first thing is make the unit same, and it is always easy to handle tex units. They become easy to comprehend and solutions also become quite faster and easy. So, first what we should do in this case, we will convert Ne to tex. So, tex value of the slivers will be 590.5 by 0.1, that is 5905 tex, and for the other sliver is going to be 590.5 by 0.12, that is 4920.8 tex. So, these are the tex values of the input slivers. All right. This you have to remember. Now, total input sliver linear density is how much? Because we are feeding 4 slivers of 0.10 Ne and 2 slivers of 0.12 Ne. That means, it is going to be 4 into 5905 plus 2 into 4920.8. So, if we do this, multiply and then add them together, we get a value 33461.6 tex. Convert them into kilotex, it becomes 33.461 kilotex, that becomes the value. So, this is what the combined linear density of 6 slivers at the input stage to the drafting unit. Now, from there I have to get a sliver of 5.5 kilotex. So, 33.46 kilotex to 5.5 kilotex, this is the change. Total combined 33.46, the output has to be 5.5. How much draft we need? We simply take the ratio. So, 33.46 by 5.5, because both are in kilotex. So, the units are same, we simply take the ratio. If we take the ratio, we get a figure 6.0838, that means it is close to 6. For all practical purpose, we should say it is close to 6. So, the drop that we need to produce 5.5 kilotex sliver is 6 in this case. Now, there is another continuation of the same problem. What it says? If the sliver combination is changed to one sliver of 0.10 Ne and 5 slivers of 0.12 Ne. So, now earlier there was some combination, this time we have some other combinations. So, there is a change in combinations now. What will be the drop to produce the sliver of same linear density? So, the approach will be very same, whatever approach we had adopted earlier, the same approach we should follow also this time. We have one sliver of 0.10 Ne. So, it will be 1 into 5.905, rest are 0.12 Ne. So, 5 into 4920.8. We find out the total text value of the input slivers. This is the total sliver linear density at the input stage. That gives you a figure which is 3509 text, and written in kilotex form is going to be 30.509. So, total sliver linear density at the input is going to be 30.5 kilotex. Output kilotex is no change, is 5.5. So, if we want to know the drop, you simply take the ratio input density linear density to output linear density. So, it is 30.509 divided by 5.5, and that gives you a value 5.547. So, approximately we need a drop of 5.5. So, this is what the drop which was required when we change the sliver combinations. So, you see that as you go for more number of finer slivers, 0.212 Ne sliver, it will finer than 0.10 Ne sliver. So, when I reduce the coarser sliver and increase the number of finer sliver, the drop that I need to produce a sliver of same linear density is obviously going to be less. Once you know complete your calculations, you also try to think logically that whether the final answer should be less than the previous answer or more than the previous answer. And if we try to logically understand this, that the figure has to be less or has to be more, whatever the, whatever is the situation, then you can you could be doubly sure that your answer is correct. And in this case, because I am adding more number of finer slivers and reducing a coarser sliver, but I am keeping the final sliver count same, therefore, the drop must be less. And if we compare the previous answer with this answer, so previous answer was how much? Let us go back. Previous answer was 6, and now this answer is now 5.5. That means, there is a reduction in drop, and which is logically also correct. Therefore, we are sure that my answer is going to be correct. Okay. So, from there we go to another problem now. Read the problem. 2 polyester and 6 viscose rayon slivers of same count are blended on a draw frame. 2 and 6 counts are same. Okay. In the second passage, 4 slivers from the first passage are further blended with 200% viscose rayon slivers of the same count. Determine viscose percentage in the final sliver. So, this problem is little similar to the one problem we have discussed earlier. In that case, we introduce cotton sliver at the second drop frame stage, but here we are not introducing cotton sliver, this is a PV sliver. So, we first blended polyester and viscose on the very first drop frame, that is the breaker drop frame, and then at the second stage we are introducing only 2 100% viscose rayon fibers, rest are PV sliver that we have already produced. So, if you have already if you can remember the way we solved the previous problems, then this problem also can be solved. So, solution is in this case as shown here. The only thing that we have not given any count, only numbers are given. So, there is no count value of the sliver or linear density value of the count sliver that is given in this particular problem, only numbers are given. So, let us assume that the sliver linear density at the beginning be x kilot x and all slivers are of same count, that is what has been stated in the problem itself, the numerical, because you see slivers of same count. So, there is no change of count, that is to your advantage. So, let us assume that they are all x kilot x. Now, total linear density of 2 polyester and 6 viscose rayon or viscose slivers right at the beginning when you feed them on the first drop frame is going to be 2x plus 6x, that is going to be 8x, that is it is going to be 8x kilot x. Now, once we give the first passage, the proportion of polyester in the blended sliver is going to be 2x by 8x, that is 0.25, and that is why it will be 25%. So, the proportion will be decided on the basis of numbers, since the counts remain same. So, 2x by 8x, that gives you 0.25. So, proportion of viscose is going to be 100 minus 0.25, that is going to be 0.75 or 75%. So, that is how we can find out the percentage of polyester and viscose slivers after first passage. So, 25% and 75%. So, this is the first part of the problem, probably there is second part also. After second passage, linear density of the polyester part in the slivers is going to be how much? This is what we have to decide now. We are feeding 4 slivers and each PV sliver is containing 0.25 proportion of polyester. So, if I feed 4 slivers, in the 4 slivers the total linear density of the polyester part is going to be 4 into 0.25 into x, that is going to be 1 x, or that is what is x, because each PV sliver is containing 0.25 proportion of polyester, and if I feed 4 of them together, the 4 of them will have a total linear density of 4 into 0.25 into x. So, it is going to be x only. So, linear density of the viscose rayon part, how much? 4, we are feeding each of them is containing 0.75 proportion of viscose rayon. So, it is going to be 4 into 0.75 x plus 2 new slivers, 2 viscose rayon fibers of 100% viscose rayon is being fed. So, that will be 2 x. Therefore, total linear density of the viscose part in the feed is going to be 4 into 0.75 x plus 2 x, that will give you a figure 5 x. So, that means, at the feed point we have x of polyester and 5 x of viscose rayon. So, proportion of polyester in the final blended sliver is going to be how much? X by 6 x is 1 upon 6, which is going to be 0.166. So, polyester is going to be 16.6% if we convert them into percentage, and proportion of viscose similarly if we try to find out. So, we have 5x viscose and total sum of mass of all the saliva is going to be 6x. So, 5x by 6x. So, 6x is coming because combined linear density of all the salivas fed is going to be 6x. So, 5x by 6x, that ratio gives you a figure 0.833, and if we convert them into percentage, then we get a value 83.3%. That means, we finally arrive at the value that we get 16.6% polyester and 83.3% viscose rayon in this case. So, this is how the percentage of polyester and viscose in the fine lens slivers can be changed, and that is what sometimes we have to resort to in an industrial situation. It is not that we will always feed PV, polyester and viscose in the same ratio the first passage and the second passage. Depending upon the need, sometimes we have to arrive at the right percentage of polyester and viscose by adjusting the number of polyester and viscose slivers, and also many a times their count, and at the first draw frame stage and also at the second draw frame stage. This is what is practiced many times. With this, we close this particular session on numericals. So, you could see that we have solved quite a few numericals and do it several times, and generally the nature of the numericals, it appears to be really quite simple. They are not very difficult and mostly based on simple arithmetic. Only the conceptual clarity should be there, and the accuracy in terms of basically calculation accuracy should be there. Since you all are used to calculators, so that is not a really big problem, calculation part. If the conceptual part is clear, you will be able to solve the problem. Most of the problems are otherwise very, very simple. They are not difficult at all, but try to understand the concepts and then you will be able to solve. There is no problem at all. Thank you.